Hey everyone, and welcome to my presentation. Today I'm going to do a quick popular science presentation on the radial velocity method for exoplanet detection. There's no real need to have a big physics, science, or math background, and I'll introduce all the major concepts. So just sit back and enjoy. Anyways, let's get started. Alright, so the first thing we need to do then is define what an exoplanet is. Here, that's literally just any planet in the entire universe that orbits a star other than the sun. The keyword there being orbit. So what's an orbit? An orbit is just any circular or elliptical path that one celestial body regularly takes around another. And we normally, in physics, say that this is due to the bending of space-time, a la the figure in the top right. I won't get into the time dilation part here, but how the bending of space affects orbits can be pretty easily visualized using a metaphor called Newton's cannon. And that's relatively simple. The idea is that you take a cannon, you stick it at the top of a very tall mountain. For low velocities of your cannonball, it's just going to fall right back to Earth. But there's a catch. The Earth is actually curving underneath the cannonball as well. So there are particular velocities that the cannonball might achieve for which the Earth will curve underneath the cannonball faster than the cannonball falls, right? In that case, we say that we have a stable orbit, and it will form a circle or an ellipse, unless it's going too fast, in which case you have escape velocity and it just flies off. Originally, we believed that the Earth was the center of the universe and that the sun, moon, stars, everything orbited around it. But then we discovered a much simpler model where we put the sun at the center of our solar system, and things got a lot better behaved. Unfortunately, that's also not a very good model. You see, gravity is actually a two-way force. So any two massive objects will attract each other. And this means that actually objects orbit around their common center of mass, similar to a seesaw. Just as a quick aside, for fun, the Earth-Moon system has its so-called barycenter about 75% of the way out from the center of the Earth. But larger planets like Jupiter actually have their barycenter outside of the sun. Other systems like the Pluto-Charon system it's difficult to even say one is orbiting the other. Really, the actual thing that's happening is that the two bodies are orbiting around their common center of mass. And this is important, as you'll see later on. The final piece of the puzzle that we're going to need to understand this is the so-called Doppler effect. Basically, this just says that anything that emits a frequency and which is moving towards an observer will experience a higher frequency oscillation. As you can see in this quick little animation, basically what happens is the car is a honking, and as it starts moving forward, the sound waves in the forward direction are compressed, while the sound waves in the back are expanded. Light is also a wave, similar to an acoustic wave, except it's an electromagnetic wave. That means a lot of things, but for now, the important part is just to know that higher frequencies of light are blue and lower frequencies are red. So we call it a blue shift in the forward direction and a red shift in the opposing direction. Now, if we look back to this idea of the two stellar objects orbiting their common center of mass, that means that the star, which emits light, will sometimes be moving towards you and sometimes be moving away from you. This means that sometimes the light will be blue shifted, while sometimes the light will be red shifted. This is key. So let's take a little bit of a deeper dive now into what kind of light actually comes from the sun. As we know, temperature is a measure of the thermal energy in a system, where thermal energy means basically just an average of the random kinetic energy in the system. And because atoms have a negatively charged outside shell and a positive nucleus, that means that random motion of these atoms will produce electromagnetic waves. You probably already knew this, though. This is what happens when an object starts to glow from red, orange to white as it heats up. Fortunately for us, there is also a cool outer shell of gas around the star, which produces very, very fine absorption lines. The random nature of how blackbody radiation is generated makes it pretty useless for measuring these small, minute red shifts and blue shifts, but these absorption lines, well, that's something we can work with. So let's put it all together then. In this figure on the left, we see that we have a planet of some kind that's orbiting a star. By that, really what I mean is that the two are orbiting their common center of mass. This means that sometimes the star will be moving towards you and the light from it will be blue shifted, while sometimes the star will be moving away from you and its light will be red shifted. If we can figure out the periodicity of this process, and if we can calculate the minute changes in the frequency of light due to this Doppler effect, then we can tease out some information about the exoplanet. And that's how it works. That's the radial velocity method. That's how we find planets around other stars. Well, it's one of the ways at least. So how is all of this related to what I do? Because, as most of you probably know, I am not an astrophysicist. I'm an optical physicist and I study quantum and nonlinear optics. In particular, what I do is build something called a frequency comb. A frequency comb is a particular type of very, very low noise and highly predictable laser, which is made up of lots and lots and lots of distinct frequencies. Really, you can think of it as an optical ruler. Basically, the laser I make has lots of little tiny tick marks, each one representing a very well-known optical frequency. If we take this optical ruler and we lay it on top of the recovered spectrograms, then we can much better calibrate the system. This allows us to get better measurements about the very small red and blue shifts that we recover and helps us, well, better understand what's happening. So that's what I do, basically. I build optical rulers that help to calibrate systems that will detect exoplanets. If anyone has any questions, I can open up to you. There's a lot of cool stuff we could be talking about. I talked about how light's an electromagnetic wave. Maybe you're curious about how that works for the human brain, how vision works, rods, cones. Maybe you're interested in blackbody radiation and how that relates to the ultraviolet catastrophe and the discovery of quantum mechanics. Who knows? I'm an open book, and the rest of it's on you guys. Thanks for showing up, and if anyone wants to dip out now, feel free. Cheers.